Видимо, да.
Вот. Сегодня у нас выступает Юрий Аркадьевич Кордюков, и он нам расскажет про теорему Конна о следах для контактных многообразий. Пожалуйста.
Значит, на каком? На английском мне надо говорить, да?
Ну, на ваше усмотрение. В общем, говорить можно как по-русски, так и по-английски. У вас слайды по-английски же, да?
Ну, я могу... Ну, давайте я по-английски так буду говорить.
Ну, давайте, да, тем более я смотрю, today we have Martin White among our seminar, so probably it will be more convenient for him if you speak English.
Okay, so thank you very much for the invitation, and I will talk about Contra's theorem. First of all, eventually on contact manifolds, and this is joint work with Fedor Sukochev and Dmitry Zanin from Australia. And okay, this is about non-commutative geometry, and probably there is no need to talk about this at this seminar, but just in case, so this is basic sources for non-commutative geometry and his creator, Alan Kohn. And actually, I will talk one specific aspect of non-commutative geometry. So we know actually that the starting point and one of the basic points of non-commutative geometry means that we have, so we try to develop geometry of singular spaces starting from some operators, what should be operator, and so just say geometry from the spectral point of view. And to do this, sometimes it's necessary to, actually, this is rather tricky sometimes, and I will just discuss one problem, the problem of integration in non-commutative geometry, and also only just what is the motivation for definition of integration in non-commutative geometry? And the problem which I'm going to discuss is the following. Suppose we have a compact Riemannian manifold of dimension n. So here we have Riemannian metric. Then we have the corresponding operator, Laplace-Beltrami operator, and you know that actually we need Dirac operator, but for this, actually in this topic we just have square of Dirac, and this is really Laplace-Beltrami operator. So let's take a Laplace-Beltrami operator. And this is initial data, so we want to develop geometry from the spectral theory of this operator, from operator theory, from this operator in a Hilbert space. And we want to study the following question. Suppose we have a continuous function on a manifold. How can we compute the integral of this function with respect to the Riemannian volume form given by this formula, starting from the operator? Nothing more. And then you know the story actually. Then we say that, okay, we have a non-commutative space and given by some non-commutative algebra acting in a Hilbert space. The analog of Riemannian metric is so-called spectral triple, which is really a kind of Dirac type of operator. And then we say that, okay, what we have in this commutative case, we extend to non-commutative setting. But just first, I want to discuss this commutative setting. So this is the problem which I am going to discuss. Okay, so we have the operator in a Hilbert space. So this is a self-adjoint operator, and we have a function. and we want to get a number, this number from these operators. How can we really extract numbers from the operators? One tool we know, this is the trace, the usual trace in a Hilbert space. So let me recall this its definition. So suppose we have a compact operator on a Hilbert space, operator A. Let's consider its singular values, which means that these are eigenvalues of the operator absolute value of A, so square root of A star R, counted according to multiplicity. So I recall you that this operator already, so if A is compact, then this absolute value of A is a compact self-adjoint operator, and by Hilbert's theorem we have a complete basis of eigenvalues, of eigenfunctions with eigenvalues going to 0. And we just take these eigenvalues, and these are singular values of a compact operator. Then we know that we have a Chatain class ideal, so this is an analog of a non-commutative analog of L1 space, and it consists of trace class operators. So one of definitions of this is just so this norm should be finite. And this is an ideal in the algebra of all bounded or linear bounded operators in a Hilbert space. And then the trace is defined in this way. So yes, so this is the sum of diagonal matrix elements in any orthogonal base. So this is we know this. And there is a Litsky theorem. There is a deep Litsky theorem which says that in case of positive, so this is the same in case of positive operators. This is the same as a sum of eigenvalues. Well, not even singular values. Just this is a sum of eigenvalues of this operator. And the important point of this functional is a trace property, which is given by this formula. And this is very convenient in many cases. And so, okay, everybody I think knows this, and just this is just to start with. But let me recall now what happens in geometric cases. So geometrically defined operators are pseudodifferential operators. So suppose again we have a compact smooth manifold of dimension n. Then we can consider classical pseudodifferential operators of order m, which means that in each local coordinate, this operator is given by this formula. For instance, if A is polynomial in Xi, this is just a differential operator. But for pseudo-differential operators, this is just like converse of elliptic differential operators, or maybe complex powers of them. So this A is not a polynomial, but a kind of polynomial-like. So the complete symbol is an asymptotic sum of homogeneous components. So A is represented as a sum of homogeneous components. So HAM of J is a homogeneous function of degree m minus G for Xi large enough. So m minus 1, this goes to infinity. M may be negative, so m actually should be negative because we are talking mainly about integral operators, so operators of negative order. And what we know that if A is a pseudo-differential operator, and the order of this operator is less than minus dimension of the manifold, then this operator is a trace class operator. Actually, in this trace is given by the very well-known formula. So this is the integral of the kernel over the diagonal with respect to some fixed volume form. And the kernel is just the Schwarz kernel of this operator. So you see this just. And in this case, when m is less than minus n, the kernel is just a continuous function. So the integral is well defined. Because typically when m equals 0, I will talk about this later, these are so-called singular integral operators. They have singularity near the diagonal, but the kernel of this operator typically is smooth outside of diagonal. This is pseudo-locality property of pseudo-differential operators. So this, you see, so this, if m is small enough, the degree of the operator is, order of the operator is small enough, then the operator is trace class operator. Okay, but it is not enough for us. We need more, but for a long time people were thinking that there is nothing more. And actually, Dixmier also was thought of this for a long time, that there is no trace. So this is the only trace on algebra of on operators. But then in 1966, Dixmier discovered that there are much more traces on some algebras of operators. And these are quite exotic traces, and now I will talk about this. They are non-normal and they are singular traces. So first of all, we should consider so-called weak Chataine class, or sometimes it's called Matsayev ideal, L1 infinity. So this class consists of compact operators in a Hilbert space with this norm is finite. And this is again an ideal of the algebra of linear bounded operators. And then we need to, and then we have so this sequence is a bounded sequence, but it's not convergent. But then we should find a limit of this. And we do this just in the following way. So we take the usual limit, extend it to the space of bounded so infinity of all bounded sequences. So let's consider any extension of this limit of the usual limit to such a functional linear functional, which is dilation invariant and positive. So which means the following. So the limit is non-negative is all terms of the sequence are non-negative. It coincides with the usual limit when the ordinary limit when the usual limit exists. And this dilation invariant means that if we double the sequence in the following way, so we take each term twice, then this exotic limit will be the same. And once we have such a extension, there are many extensions of this, and there are a series of so-called Banach limits, which are particular cases of this. Then we can define the corresponding linear functional in the following way. So we have a bounded, by definition, we have a bounded sequence, and we take this limit and we get a number. So we fix such a, so we get a linear functional on this weak Chataine class. And what's interesting that this we get in this way, we really get a trace. So this function now is a trace. So trace of AB equals trace of BR. This is very good. But then this trace really lives on a different space, on a different class of operators than the usual trace. So actually each Dixmuir trace, so I call this, this is each functional Dixmuir trace. Each Dixmuir trace vanishes on trace class operators. By this reason, sometimes we will call that this is a singular trace. So, so this is 0. And this trace is not normal, is non-normal. So this is the standard property of the usual trace. So normal, semi-finite, faithful. It's this is standard properties of traces von Neumann algebras. But here not. So I remind you that a trace is normal is for any increasing net of operators with some limit, we have the corresponding convergence of traces. Only for increasing nets, not for any convergent set. Convergent nets. And there is no, so these traces are non-normal. And there are plenty of them.
I'm sorry, so your omega is a sort of filter in the subset or ultra filter. What does omega mean in your context?
Omega means just notation for this, nothing more, just notation for this functional.
Ah, okay, any limit line. Okay.
Yeah, no, yeah. Just this is just a notation for any functional of this kind.
Okay, thanks.
And okay, this was in 1996, but this was just by curiosity, and then only in 1988 there was a theorem by Alencon, and who proved that if we take now a pseudodifferential operator of order exactly minus n. You remember that for trace class operators, I consider it operators less than minus n. Then it turns out that each operator belongs to this weak-Schatten ideal, weak-Schatten class, and for any extension, for any omega or lim omega, the corresponding Dixmuir trace is the same. And moreover, this Dixmuir trace coincides with another trace on the algebra of pseudodifferential operators, which actually appeared in a different way in a different field of mathematics. So this is so-called Wadzicki noncommutative residue. And Wadzicki noncommutative residue really has less this functional analysis. It's more geometrical because it deals with pseudodifferential operators. And this is really, so it is defined in the following way. So we have a pseudodifferential operator. I recall you that if we have pseudodifferential operator, then its complete symbol is an asymptotic sum of homogeneous components. We should take the we should take some appropriate homogeneous component of degree minus n exactly as this is the minus n dimension of the manifold. And it turns out that this quantity, so multiplied by dx dxi, will be a well-defined density on this cosphere bundle, and you can integrate. So this quantity is well-defined and is independent of the choice of local coordinates. And what is remarkable is that this is the trace on the algebra of pseudo-differential operators of any order. Maybe positives so of any integer order. And this is this was proven by Mario Schwarzitsky in 1984. This was his habilitation thesis or doctoral thesis in Stiklov Institute, and he was a student of Yuri Ivanovich Manin. And actually, before this, there was purely algebraic theorem about traces on algebra of formal pseudo-differential operators in one dimension. And this was suggested by Adler and independently by Adler and Manin. So Adler-Manin trace on formal pseudo-differential operators in one dimension. And this is high-dimensional extension of this theorem. And then there was also a paper by Victor Gaimin, so Wadzicki 1984, 85. He also suggested this non-commutative residue. And so you see, and it turns out that this, so what we have again a kind of what trace formula. What does it mean? So on the left-hand side, we have really something very functional analytic. So only defined in terms of operator theory, in terms of eigenvalues of an operator, of the operator. On the left-hand side, we have something which is defined in terms of principal symbol of complete symbol of operator, in terms of, in some sense, in terms of geometry. So pseudo-differential operator is geometrically defined operator, and really we have something related with geometry. And actually, this formula enables us to answer to the question which I posed in the beginning. How can we recover the integral from the Laplace-Beltrami operator? And this is a Kohn integration theorem. Okay, so let's now again consider a compact Riemannian manifold. Consider Laplace-Beltrami operator as before. Then if we take this power minus n over 2, so then this second order operator, so this is will be, one can show that this is exactly the operator of order minus n. So if we multiply, so if we take the composition of this operator with multiplication of operator by a function f, smooth function, then we get a pseudo-differential operator again. So and by the previous theorem, it is it belongs to the Weak-Chatain class, and this is the formula. So this, you see here we have only operator in some functional analysis. And in the right-hand side, we have the integral of the function with respect to the Riemannian volume form. This is a way how we can compute this integral, starting only from operator in a Hilbert, from this operator in a Hilbert space. And this was proven in this paper by Alan Kohn, the action functional in non-commutative geometry in CMP in 1988. And this really give this gives really give motivation how we can define this integral in non-commutative geometry. So in non-commutative geometry, we start with the spectral triple. We have an analog of Dirac operator, and as well as an analog of this Laplace-Beltrami operator. So just the square of the Dirac operator. And then we can take this. We can take the left-hand side of this formula and say that this is really an analog. So this is a non-commutative integral in non-commutative geometry. Once we have this, once we know how can we integrate in non-commutative geometry, we can say that when we can define many physical quantities like actional, functional, so like in Young-Mills theory, and then the next step was for Allen Kohn to define actional, functional for some so as a model for standard as an example. He got a standard model for in quantum physics. This is a famous paper by Kohn and Lott. And then really we can, well, yes, but we can also consider not only multiplication operators, but we can also consider any pseudo-differential operator for the zero. So multiplication operator by function. So multiplication operator by function is an operator of such type. But if we take any pseudo-differential operator, so we have the principal symbol of this operator. So this is just, again, the principal symbol is the top degree homogeneous component of this asymptotic expansion, as I showed you. And for if you have multiplication by functions, then there is no dependence of xi. So a naught of x xi equals f of x. But in general, one can show that the principal symbol of pseudo-differential operator is a smooth function on the cotangent bundle, is a well-defined smooth function on the cotangent bundle. So xi should be understood as coordinates of a covector, which is homogeneous of degree 0. So homogeneity remains. And thus we have the principal symbol mapping. This is a star homomorphism of involutive algebras. So algebra of pseudo-differential operators and algebra of smooth functions of on the cosphere bundle, which is the same as the algebra of homogeneous function of degree 0. So there is a natural action of the real line of t on t star x. So we just by multiplication, and then the formula of Kohn trace formula gives us the following formula. So here we have t operator t multiplied by this degree of this Laplacian. But here we have integral of the principal symbol, with respect to the Liouville volume form. And then there are two very natural questions which arise. So can we put something different? Can we put something different instead of these traces? So how can we extend this trace, this set of singular traces, for such that this formula holds? And also, can we extend the set of these operators? Maybe taking something more. And there was a large activity after this paper by Allen Kohn, and actually the proof of Kohn was very very telegraphic, as some people say. So very sketchy, and you should put them. So there was a large activity, and actually my co-authors are just two well-known experts in this theory. So they wrote a book on these singular traces. And there is a second edition in 2 volumes, which just appeared last 2 years. So instead of Dixmuir traces, we can consider such a much general objects. Of course, we should consider traces. So here I just recalled again the definition of the trace. So phi, we instead of trace Dixmuir trace, we can consider a linear function, a linear function of phi, which is a trace. So as I said already, as I have already said, the singular trace means that it vanishes on trace class operators. Then we should assume that phi is continuous with respect to this quasi norm on this space, and some normalization condition which holds for each Dixmuir trace. So this is what really we will have instead of Dixmuir trace. So instead of Dixmuir traces, we will have continuous normalized traces on of this type. What should we have instead of operators? How can we extend the set of operators? Actually, we can consider the closure of this algebra of zero-order pseudodifferential operator. So any operator, any zero-order pseudodifferential operator defines a bounded operator in the L2 space. Then we can take uniform closure, and this will be a cyst algebra. Moreover, one can show that the principal symbol map extends to a surjective star homomorphism of the corresponding cyst algebras. So we have surjectivity at this level. So any continuous functions function can be lifted to the closure, and the kernel of this symbol map is just the algebra of compact operators. So in homological language, we have a short exact sequence, which is which first appeared in Atya Zinger paper, and it plays an important role in index theory. So we know that we can. So the standard way how to use this short exact sequence is to consider so-called 6-term long exact sequence. So we can consider cohomological long exact sequence, and then recall that we have both periodicity. So instead of infinite long exact sequence, we have just 6-term exact sequence, and some maps, this is just index maps, and this is one way how defined index map in K-theory. But on the other hand, these two facts, or this fact that we have a short exact sequence, is essentially equivalent to the fact that if we have any operator which is in this closure of zero-order pseudodifferential operators with the principal symbol, then really this quotient norm is just the rate of best approximation of the operator by compacts. And it turns out that the best approximation is just given by the norm, by the uniform norm of the principal symbol. And actually, so in this way, approximation by compact operators was very important in operator theory, and even before pseudodifferential operators in index theory. So this because the theory of pseudodifferential operators appeared after the theory of singular integral operators. And for singular integral operators, this result was proved by Gochberg in 1962. And sometimes this fact in this theory is called Gochberg lemma. But then Seeley has another proof in the paper of 1966, and Atya Zinger, this was really done, I think this was done for index theory, and motivation for Atiyah Zinger, of course. Okay, so this we have such a system algebra, and now we can formulate the more extended formula which we have in this case. As I said, now we have actually contrast theorem. When instead of each Dixmuir trace, we have just every normalized continuous trace on this L1 infinity. And instead of t, so we can take t, just the corresponding, just any operator from this system algebra. And there is another, and the answer is actually the same, but it's quite convenient, not even convenient, but it's better to write the answer not as an integral with respect to the Liouville measure on the cosphere bundle, but go back to the entire cotangent bundle, introducing such a weight. We call this canonical weight. Well, it's quite typical for proper action. So when we have a proper action of a Lie group, we can put some functions, cutoff function along the orbit of this group, which with the integral equals 1, and that's what really is done here. So if we consider, if we pass to polar coordinates and integrate with respect to radius, we get just integral of Gaussian, nothing more. But it will be very useful for us further when I will talk about contact manifolds. So this is really very classical stuff, and this was really yes, again, big work by Fedor and Dima, by Fedor Sukochev and Dmitry Zanin, of course, first of all. But then I am going to talk about is an elliptic operator, and it in elliptic operator in equation if we fix this linear equation at each point, we get differential one form, theta, which which vanishes at this age. Then the condition of there is a condition of this theta. So if we take theta one is a one form. I take d theta. This is going to be two form. And I take such an exterior product. So I take one form once and two form d theta d times. So this is 2d plus one form. So this is the volume form on the manifold. And the assumption that this volume form is nowhere vanishing. And this is the definition of a contact manifold. And Actually, there are several sources of such contact manifolds. First of all, classical mechanics, where actually we know that in classical mechanics, the phase space is a symplectic manifold. So a symplectic manifold is odd, not odd, but even dimensional manifold equipped with a differential two form, which is closed and not degenerate. Actually, contact manifolds are odd dimension analogs of these symplectic manifolds. For instance, if we take a surface in this in a phase space, to say energy surface of mechanical system, we then we get such a contact manifold. Then we have another source of even dimensional manifolds, which are given by complex analysis. So in complex analysis, each manifold is even dimensional if we consider real dimension. And again, if we consider surface, hypersurface in this odd even dimensional manifold, we sometimes get contact manifolds. And actually, this happens if we consider complex manifolds with strictly pseudo-convex boundary. So the boundary of convex domains are contact manifolds. And it was generalized, so these are so-called Cauchy-Riemann structures of Cauchy-Riemann dimension 1 with non-degenerate Levy form. So non-degeneracy Levy form is related with this fact of non-degeneracy of this volume form. And again, in sub-Riemannian geometry, this is the simplest example of sub-Riemannian manifold. In sub-Riemannian geometry, we consider again a main object is a manifold with a distribution. And we should have a so-called bracket generating condition, which means that commutator of vector fields tangent to H with two vector fields tangent to H should generate all vector fields. So not every vector field to the manifold is tangent to H. But any vector field can be represented as a sum of vector fields tangent to H and vector field which is commutator of such fields. And this is the simplest example of sub-Riemannian manifold. These are the three sources of contact manifolds. And the standard example, this Heisenberg Lie group. So this is the definition of this. We know sometimes it's more familiar definition as a set of certain upper triangular matrices. But we can also, this is another way to define the Heisenberg group, like such a symmetric way to do this. So I consider such pairs, such tuples of, so Z and T, Z belongs to CD, and T is a real number. And this is multiplication on this set. And one can also consider the corresponding real notation. And the contact structure on this Heisenberg group is given by this differential form. Actually, again, this is in classical mechanics, we know that there is a symplectic form is dp/dq, and one form p/dq, and t. So this looks like this, and t looks like the time. So one can check that this 2D plus 1 form is not degenerate. And what's important about Heisenberg group, then this is really a model example for a contact manifold. We know that for symplectic manifold, each a local model is given by just the standard phase space of classical mechanics. So with coordinates and impulse momentum, so P and Q. But for contact manifolds, this is given by Heisenberg group. And yes, and the fact that this is a local model is given by Darboux theorem. And the corresponding Darboux theorem we have in this case. But first, okay, yes, but first let me recall you also, yes, recall you about operators. So once we have a Lie group, we have the corresponding Lie algebra, and Lie algebra is given by these operators. So this is a natural basis of the Lie algebra or left invariant vector field. So these are commutator relations. We see that here we really have a kind of canonical commutation relations. And hyperplane bundle H is spanned by these vectors x and y. And one can check that theta vanishes on this vector fields. And then we can consider this corresponding Laplacian taking just the sum of squares of this axis, no t, only x and y. And this is a famous sum of square operator. So this operator is not elliptic because we don't take the x 2d plus 1. We have derivations only along with respect to directions of h. But it turns out that because of this bracket generating property that the that you see here, when we take a commutator x and y, we have t. So there is no t among x and y, but t appears as the commutator of x and y. And this simplest bracket generated property in this case tells us that this operator is hyperelliptic. And hyperelliptic means that if we consider the corresponding equation, so delta u equals f, if the right hand side is smooth, then the solution will be also smooth. And this holds locally. So this is typical for elliptic equations, but this also may be true for some non-elliptic equations, and this property is called hyperellipticity. And I will talk maybe about this maybe later, but just tell you that this is so. And actually, in complex analysis, actually this appeared in complex analysis. As I told you, that one of the basic example is the boundary of the boundary of strictly pseudo-complex domain. And in this theory, Heisenberg group appeared as a model for the boundary. So there are certain so-called Chern-Moser theorem, Chern-Moser normal forms, which says that this boundary can be approximated by Heisenberg group. And then certain certain operators like Debye operator, so boundary Dalbo operator, and the corresponding Laplacian turn out to be non-elliptic operators, but like this sum of squared, only hyperelliptic operators. And this gives a very strong motivation for development of this theory in 70s. So there were papers by Rothschildstein, Follenstein, and more, where this was originated really in complex analysis. But I will talk about this when so this is just for the local model. And as I told you already that there is Darboux theorem, so which tells us that this Heisenberg group is a local model for a contact manifold. So actually on each contact manifold there exists so-called Heisenberg atlas. So an atlas which consists of these charts, and moreover, each transition function, each diffeomorphism which relates these two charts is a Heisenberg diffeomorphism, which means that it preserves a contact structure. So it preserves this hyperplane H. So once we have this homeomorphism, we have, and if we identify this space with the Heisenberg group, we have some hyperplane here. We can transfer this hyperplane here. We can transfer, and actually yes, and this phi g just preserves this hyperplane, which this means that it is a Heisenberg or contactomorphism. And one can show that we can always, at each point, we can say that the part of a contact manifold is a Heisenberg group. And once we have this, we can take all these objects which we have on the Heisenberg group and transfer them to the contact manifold. And then what we need more, we need I am thinking about operators, and of course when I take the sum of squares, which means that we have a kind of metric. But this means that, and this is called sub-Riemannian structure. So in geometrical language, sub-Riemannian structure is a smooth inner product in the fibers of this H. So we just fix inner product in each fiber, in each hyperplane, and it should depend smoothly on a point. Of course, once we have this Heisenberg atlas, then we have this vector fields axis, x1, x2, x2d, and we can write this we can take the corresponding matrix of this this scalar product, which gives us in a usual way matrix will be 2d times 2d square matrix which is positive definite. Okay? And then we define actually the operator first in each chart, and then we glue them. But there is one important thing which which we really don't have in this setting. Yeah, and actually, we don't have this in a sub-Riemannian setting. When we have a Riemannian metric, then we automatically have a Riemannian volume form. But in this case, we don't have actually for contact manifold. We can discuss what and actually this one of our purposes to know what do we mean about this volume form. But actually, we don't have a canonical volume form. And here, this is the formula for the Laplace-Beltrami operator. This square root of determinant of G, this is really reminds us of the volume form. And by this reason, we should fix additionally. So when we talk about sub-Laplacian, about analog of the Laplacian on a contact manifold, we should fix not only this sub-Riemannian structure, but also additionally we should fix a positive smooth density. Density, roughly speaking, means volume form. So positive, smooth positive form of top degree. And then we fixing this, we define this sub-Laplacian locally in this way. So we have a basis which is given by this. We have so as I said, once we have this Heisenberg chat, we have some distinguished basis on the Heisenberg group, and we can consider them. That's what we are doing here. And we multiply it by inverse elements of this matrix which we have from sub-Riemannian structure. And then we take a formal adjoint of this operator. This is a first order differential operator. We take a formal adjoint and we get an operator. Okay, and actually this is let me see that in this well-known definition we do the same. Because this definition of the Laplace-Beltrami operator can be also written in this way. Because here, first we see here, we see here d over this derivative with respect to xl, which is just xl. Then we multiply by these coefficients. And what remains here, actually, this is a joint of this operator. So this formula can be rewritten exactly in the same way as this formula. And so that yes, and this is this allows us to write the definition of the sub-Laplacian only just in operated theoretical language. And then one can show that these operators can be glued. These are locally defined operators. So these operators, these are locally defined operators, can be glued into a unique second-order differential operator, which depends both on the sub-Riemannian structure and on this positive density nu. And this is the second-order operator. One can show that this operator is self-adjoint. This is actually this operator is self-adjoint, so it has it is essentially self-adjoint. So if we take the closure of this operator in the L2 space, we get a self-adjoint operator in a Hilbert space, and this operator has discrete spectrum, which means that this operator has a complete orthogonal system of eigenfunctions, and the corresponding eigenvalues goes to infinity when, and each eigenvalue has finite multiplicity. So these two properties exactly this really for these two properties is very important that we have this hyperellipticity. So we don't have ellipticity, but hyperellipticity allows us to show these important properties of the operator. So again, we have an elliptic differential operator with discrete spectrum, and then we can ask, okay, what kind of trace formula, analog of the contrace formula, can we have for this operator? And what do we have for the corresponding volume form? And this is the answer. And so again, so you see, what we do here. Again, we take this operator. So, well, it's clear that one plus the Laplacian is just a positive operator. Adding one gives us a strictly positive operator, so there is no problem with taking powers, negative powers of this operator. We multiply this by any continuous function. And this is really again, some Meller formula for harmonic oscillator is hidden here, but yes, and so this is this is an analog of Riemannian, so-called Riemannian volume form in this spectrally correct Riemannian sub-Riemannian volume for contact manifold. Okay, so this is just for multiplication functions, but let me talk now about pseudodifferential operators. And actually, this is another story which I was not talking about yet, that actually the goal was not only to give the proof of the contrace formula, but also to give a kind of definition of pseudodifferential operators from the point of operator theory and noncommutative geometry, maybe. So we know, and I told you that the usual definition of the pseudodifferential operators is given by Fourier, is based on Fourier transform very much. But say if we are talking about Heisenberg, already Heisenberg group, and more generally, and in more sophisticated cases, Fourier transform is not very useful and very efficient. And actually, what we developed even in the classical case of smooth manifolds, and this was the addition, and this was the initial idea of my collaborators, of Fyodor Sukochev and Dmitry Zanin. They were trying to develop such a operators or C-star algebraic approach to pseudodifferential calculus. And actually, but actually this is done not only for not for the algebra. Actually, system algebraic means that we trying to construct not the algebra of psi, but the closures, which means the system algebras, not the algebras of these classical operators without closures. And this is typically pseudo-differential operators were developed also in this hyperellipticity stuff for regularity properties of solutions of some equations and so on. But this approach intended more on index theory. And then system algebra, so system algebraic approach maybe in many cases is more appropriate and more efficient. And the starting point for the Heisenberg, so for pseudo-differential calculus on the Heisenberg group, and for the Euclidean space as well, is so-called Riesz transform, which is defined by this operator. So we take this sub-Laplacian, take degree of -1/2 and multiply by x. So if we are in the Hilbert space, in a Euclidean space, this operator after Fourier transform would be psi of k over modulo psi, some building block of zero-order pseudo-differential operators. But in here we have this operator. Just take this operator. So one can show that this Riesz transform operators satisfy many important properties. But they are very tricky because you see this sub-Laplacian is not strictly positive. It's just positive, but not strictly zero in the spectrum of this operator. But anyway, and then we just take this system algebra generated by this operator. These are bounded operators in L2, again like singular integral operators, so zero order. And then we just take this operator, multiply by any. So in some sense, if I am talking about usual pseudo-differential operators, their symbols depends on x and psi, and they are generated by products, functions of x here, and functions of psi. And functions of psi, these building blocks for them, just these Riesz transforms. So then we just take products of these operators and generate system algebra. And this is a pseudo-differential calculus on the Heisenberg. This is an analog of this closure of psi naught for the Heisenberg group. But, well, since this is just system algebra, but something remains. And what remains, this is the principal symbol. And the principal symbol is, again, a surjective homomorphism of this algebra into some other algebra. Actually, this is the algebra of functions on the Heisenberg group with values in this system algebra. So unlike the Euclidean case, the principal symbol of these operators, principal symbols are non-commutative. So they belong to a non-commutative algebra. But anyway, again, we have this prop. So we have a surjective star homomorphism whose kernel is just the algebra of compact operators. So again, we have a short exact sequence for this algebra pi with this algebra, which is a non-commutative algebra of symbols. And once we have this, we can now we can define traces on this algebra. Why do we need them. We need them because we want to integrate. As I said, you see here, these are functions of x, and these are, roughly speaking, functions of psi in a non-commutative setting. Now I want to integrate over x. I know how to do this. This is the commutative algebra. But but here I want to integrate these objects. And these are, we know, non-commutative integration theory tells us that we should consider traces. And these are really these operators are left invariant operators on the Heisenberg group. So we can consider left regular representation, the corresponding group von Neumann algebra, and there is a standard von Neumann trace on this von Neumann algebra. And this really will play the role of integration with respect to this non-commutative algebra of symbols. And once we have this, we can write now the contrast formula for pseudo-differential operators on the Heisenberg group. Exactly in the same way as we did before. So again, we consider our sub-Laplacian on the Heisenberg group. We take any S, just pseudo-differential operators, and but it should, because we are in a non-compact situation, we should consider compactly supported operators in X. And then we can prove this formula. So phi of for any normalized continuous trace on L1 infinity, we have this value is finite and equals to what? Here you see the classical formula as I explained you before. So this should be the integral of the principal symbol. We have this principal symbol. Integral with respect to dx, with this integral. And with respect to the dxi, this is von Neumann trace. And here, as I told you, that it's very convenient for us to pass from the cosphere bundle to the cotangent bundle, because we have an analog of this canonical weight, which we put it here. But this canonical weight, this was a function, but here it is an operator, just hit operator generated by this sub-Laplacian. And this operator has finite trace, and so this formula holds and makes sense. So this is an analog of contrast theorem for the Heisenberg group. So we see here some non-commutative weight function, which is just responsible for it's related with for some homogeneity indeed. Okay, this is I explained you already. And now we can once we did this for once we did this for the model case of Heisenberg group, we can glue these locally defined models into global one using Heisenberg atlas. So we take a compact contact manifold with a Heisenberg atlas. And we take just the sister algebra, which is locally, this local operator, when we have a locally defined function supported in a chat, then this operator belongs to pi, this locally defined algebra of operators. And this roughly means that outside of diagonal, this operator is compact. So as for pseudo-differential operators, really, it's important what we have near the diagonal. Outside of the diagonal, we just have compact operators, nothing more. And there are many approaches to pseudo-differential calculus or contact operators. Here some names, so classical names by Bills Greiner and Michael Taylor. and then Epstein, Melrose, some approach, some more approach, and recent approach by Van Erp and Juncken based on groupoids. Now it's very fashionable, and it's very powerful, really, to approach pseudo-differential operators using groupoids. And for these contact manifolds, this groupoid approach to pseudo-differential operators was done by Erik Van Erp and Bob Juncken very recently. And one can also construct the principal symbol mapping. And we saw that locally, principal symbol is a function on a chart with values in some noncommutative algebra. When we start to glue these objects, we get some map from our algebra of pseudo-differential operators to the algebra of to the sister algebra of continuous sections of some locally trivial bundles of sister algebras, whose typical fiber is this sister algebra generated by these Riesz transform operators. This is just quite standard but quite technical and yes, very difficult to explain shortly. And then we really get such a formula, which is really, yes, again, so on a compact contact manifold, again, the left hand side is the same, but the right hand side, again, if we compare this with this formula with what we had in the case of the Hilbert of the Heisenberg group, then we need to have something which is analog of this exponent, and we have here again some operator valued with some, as we say, canonical weight, and really this is an Qx is in some second order operator and unbounded self-adjoint positive operator affiliated with this algebra of sections of our bundle of sister algebras. And we have some faithful normal semi-finite trace on this algebra, which is obtained from these local traces. So this is again very technical, but it's quite clear how this should be. And there is also a long story. This is related with so-called local while formulas for pseudo-differential operators, and here they list some names with different approaches to some formulas and to non-commutative residues for pseudo-differential operators. But it's already quite technical, and probably I will stop here. And this just references. So this is paper in Journal Non-Commutative Geometry and the book and lecture notes in mathematics, where the first part and the second part are published. And thank you very much for your attention.
Thank you. Thank you very much for the interesting talk. Questions, please.
I want to ask about the psi minus degree n or psi or pseudo-differential operators in the Heisenberg case. Do you have definition like that to define these classes? Probably you define just psi 0, right?
Yes, in this case we don't. Yes, we only care about psi 0, the closure psi 0. Yes, so we don't have this formula analog of this formula just for. We are not talking about this formula, right?
I see. Okay.
About this formula, no. We are talking only about this formula.
Yes.
But I
And
think in different
Mhm.
approaches, these formulas exist, papers by Ponch, but maybe not with singular traces. So there are different points of view for this problem, you see.
I see. So to write down this formula, you always need the Laplace-Beltrami type operator, right?
Right.
On the right-hand side to have some volume stuff. But
Yes.
in general, we don't know, right? What might be phi trace of any operator degree 0? We don't know what is that, right? In general.
No,
You take any
well, you see, phi of 0, phi should be defined again only on this psi minus n.
Yes,
So
yes, on psi minus n, yes. In general, we don't know what is that, right? So there is no such formula for any a.
it's not
From
clear how to define them, you see, because no, that's what I don't know. No.
okay. Yeah, that's why you need this Laplace-Beltrami to generate your integral on the
Because
right.
we need the closure, yes. You see, we are talking about closure in L2, and for this we should have some functionals. So this maybe can be reformulated probably, but for psi minus n, this is not an algebra, and this is not very good, I guess.
I see, okay. Yes, thanks. Okay. Yeah, thanks for interesting talk.
Thank
It was
you.
great.
More questions, please. Well, if there are no more questions, we thank the speaker.
Okay, thank
Большое
you.
спасибо за интересный
Спасибо
доклад.
большое, да.
Вот, я прошу прощения, у меня были некоторые технические проблемы с подключением, поэтому я не могу обещать, что будет качественная
Ну, я
видеозапись.
понял, трансляция немножко это останавливалась, да, вроде бы?
Ну, у меня просто отключался интернет, поэтому вот насчет видеозаписи я не уверен. Если получится, то выложу, но, возможно, она будет неполная или какая-то поврежденная. В общем, сейчас я пока не уверен. Вот. Но, по крайней мере...
Что-то будет.
В общем, я надеюсь, что то, что у меня отключался интернет, не привело к тому, что у всех остальных тоже обрушилось. Да, по крайней мере, вроде бы не особенно... То есть, не отключалось полностью, да? Правильно я понимаю?
Ну, вроде бы да.
Ну хорошо, значит, только у меня были такие проблемы.
Но я не заметил, да понятно, но иногда слушатель, то есть докладчик может не ощущать аудиторию.
Ну ладно, в общем, будем надеяться, что серьезных проблем не было.
Запись просто прерывалась время от времени.
Ну, потому что у меня
Запись
отключался
прерывалась,
интернет.
да, это я потом понял, что это вот запись прерывается, да.
Но зато те, кто были, полностью послушали весь доклад.
Ну, хорошо, значит, в целом все было неплохо.
Это главное.
Ладно.
Спасибо большое.
Ладно, спасибо большое, спасибо.
Спасибо. Ага.
До свидания.
Всего доброго.
До свидания. До свидания.
До свидания, спасибо.
Спасибо.
До свидания.